The Industrial Revolution began in Britain around 1760. Steam power, mechanized factories, coal-driven expansion. A transformation built on innovation, capital investment, and entrepreneurial vision. Except in 1816, global temperatures dropped by 0.4 to 0.7 degrees Celsius. Crops failed across 3 continents. Yet between 1817 and 1825, the United States built the Erie Canal, 363 miles, 83 locks, designed to move cargo that didn't yet exist in volumes no one had yet produced. The infrastructure came first. The demand came later. In some cases decades later. And it wasn't isolated. This is a documentary exploration. The patterns discussed here involve historical anomalies in infrastructure development, administrative systems, and engineering scale. Multiple interpretations exist. This script presents evidence and invites examination, not certainty. The Erie Canal opened in 1825. It cost $7 million, over $150 million in today's terms. Construction began in 1817, 2 years into a global subsistence crisis. The year without a summer had devastated harvests. Food riots erupted in Europe. Grain prices spiked. Economies contracted. And yet New York State committed to the largest civil engineering project in the Western Hemisphere. The justification was future trade. The canal would connect the Great Lakes to the Atlantic, opening the interior for settlement and commerce. But in 1817, the interior was largely unsettled. The demand was theoretical. The population wasn't there yet. The goods weren't being produced yet. The canal was designed for a world that didn't exist. What's unusual isn't ambition. It's precision. The locks were standardized, 15 feet wide, 90 feet long. The dimensions weren't arbitrary. They matched something. The boats that would eventually use them were designed to fit those exact specifications. But those boats didn't exist in 1817. They were built later after the canal was finished. It's as if the infrastructure anticipated the machinery. Across the Atlantic, Britain was building rail. The Stockton and Darlington Railway opened in 1825, the same year as the Erie Canal. It was the first public railway to use steam locomotives. The line was 25 miles long, engineered for heavy freight. But here's the friction. The region it served had modest industrial output in 1825. The coal mines existed, yes. But the volume of coal the railway could move far exceeded local demand. The railway was built to a scale that made sense only if production would eventually increase dramatically. And it did. By the 1840s, the rail network expanded rapidly. Lines connected cities that had barely grown. Stations were built in towns with populations under 5,000, designed with platforms and freight capacity for much larger throughput. The infrastructure consistently preceded the economy it served. In the United States, this pattern repeats across regions. The Baltimore and Ohio Railroad began construction in 1828. It was designed to reach the Ohio River, 550 miles through mountainous terrain. The capital required was staggering. The expected freight was speculative. Baltimore's economy in 1828 didn't justify it. The western settlements the railroad aimed to serve were sparse. But the railroad was built anyway. And it was built to precise specifications. track gauge, bridge load limits, station spacing. All standardized. All anticipating a system that didn't yet exist. By the 1850s, the rail network had expanded into a continent-wide grid. Different companies, different regions, yet the systems were interoperable. Tracks matched. Freight cars transferred seamlessly. Schedules synchronized. The coordination wasn't legislated. It emerged. Then there's grain storage. In the 1840s, Chicago built grain elevators, massive vertical silos designed to store and transfer wheat in bulk. The first elevator, built in 1848, could hold 40,000 bushels. It used steam-powered conveyor systems, mechanized loading, and standardized grading. But Chicago's grain production in 1848 didn't require it. The city's agricultural hinterland was still developing. The scale of storage anticipated growth that hadn't happened yet. Within 2 decades, Chicago became the largest grain hub in the world. The infrastructure was already in place. The elevators weren't expanded. They were replicated. Dozens of identical structures, built to the same design, using the same systems. The standardization suggests something more than independent innovation. It suggests inheritance. Similar patterns appear in water systems. Philadelphia's Fairmount Water Works, completed in 1815, used steam-powered pumps to supply the city with clean water. The system's capacity far exceeded the city's population at the time. The infrastructure was designed for a city of 500,000. Philadelphia's population in 1815 was roughly 100,000. The same overengineering appears in New York, Boston, and London. Water mains, sewage systems, reservoirs, all built at scales that made economic sense only if urban populations would eventually explode. And they did. But the infrastructure came first. Electrical grids show the same anticipatory logic. Edison's Pearl Street Station opened in New York in 1882. It powered 400 lamps in a 1 square mile area. But the station's generators could supply far more. The grid design, voltage standards, distribution networks, safety protocols, was standardized from the beginning. Other cities adopted the same standards. Not because Edison mandated it, because the systems were built to interface. By 1890, electrical grids in separate cities used compatible infrastructure. Different companies, different investors, same specifications. The interoperability wasn't coincidental. What ties these examples together isn't conspiracy. It's consistency. Infrastructure built before demand. Systems designed for scale before scale existed. Standardization across regions and industries without centralized coordination. The official explanation is convergent evolution. Engineers solving similar problems arrived at similar solutions. Market forces drove standardization. Economic incentives aligned. But the timing creates friction. The Erie Canal, the Stockton Railway, Philadelphia's waterworks, Chicago's grain elevators, all built during or immediately after 1816. A year of global crisis. A year when capital was scarce, populations were contracting, and economic forecasting was primitive. Yet the infrastructure investments were massive, synchronized, and precise. The systems weren't experimental. They were implemented. By the 1830s, the United States had begun constructing a telegraph network. The first experimental line ran between Washington and Baltimore in 1844. It was 40 miles long. Within a decade, over 23,000 miles of telegraph wire crossed the country. The expansion wasn't gradual. It was systematic. Lines connected cities with populations too small to justify the cost. Stations were built in towns of 2,000 people, equipped with standardized equipment, trained operators, and codified protocols. The infrastructure assumed a volume of communication that didn't exist yet. But the system was ready when it did. What's striking isn't the speed. It's the uniformity. Telegraph companies in different states used compatible equipment. The codes were standardized. The pole spacing, wire gauge, and insulation methods were nearly identical across thousands of miles. No central authority mandated this. No federal standards existed. Yet the system functioned as if it had been designed as a whole. Britain's railway expansion shows the same architectural consistency. Between 1830 and 1850, over 6,000 miles of track were laid across England. Different companies built different lines, but the infrastructure was interchangeable. Track gauge standardized at 4 feet 5 inches. Station platforms aligned at consistent heights. Bridges were built to identical load specifications. The railways didn't just connect cities. They anticipated future routes. In rural Lancashire, a line was built through farmland in 1838. The nearest town had 3,000 residents. The station was designed with 4 platforms and freight capacity for industrial-scale shipping. The region had no industry in 1838. By 1860, textile mills covered the area. The railway was already there. The station hadn't been expanded. It had been built for what came later. The same logic appears in American port infrastructure. New Orleans rebuilt its port facilities in the 1820s, immediately after a series of devastating floods. The new docks were massively overengineered. Warehouse capacity exceeded the city's trade volume by a factor of 3. The wharves could accommodate ships larger than any in regular operation at the time. The investment made no immediate economic sense. The city was recovering from disaster. Capital was limited. Yet the port was built to specifications that assumed exponential trade growth. And trade grew. But the infrastructure was already in place. The pattern repeats in Baltimore, Philadelphia, and Charleston. Ports rebuilt or expanded in the 1820s and 1830s, designed for throughput that wouldn't materialize for decades. The docks weren't adapted. They were utilized. Then there's the question of administrative systems. By the 1840s, bureaucratic structures across the United States and Britain had begun to mirror each other. Postal systems, customs protocols, railway timetables, standardized measurements, all emerged in parallel. The U.S. Postal Service reorganized in 1829, implementing a zone-based pricing system and standardized delivery schedules. Britain's penny post launched in 1840 with nearly identical principles: flat-rate pricing, prepaid stamps, national coverage. The systems weren't copied. They developed simultaneously. Customs houses in American ports used forms nearly identical to those in Liverpool and London. The procedures, the documentation, the tariff classifications, all aligned without formal treaty or coordination. It's as if the administrative framework was inherited, not invented. Railroad scheduling reveals the same underlying structure. By 1850, railways in Britain and the eastern United States operated on synchronized timetables. Trains departed at coordinated intervals. Connections were timed to minimize layovers. The schedules assumed a level of precision that shouldn't have been possible with 1850s technology. Clocks in different cities weren't synchronized. Time zones didn't exist yet. Yet the railways functioned as if they did. The solution was administrative. Railway companies adopted railway time, a standardized clock system independent of local solar time. Different companies, different regions, same method. The coordination suggests prior agreement, but no records of such agreements exist. Industrial machinery shows similar anticipatory design. Textile mills in Massachusetts in the 1830s used power looms built to standardized dimensions. The looms were interchangeable across factories. Parts could be swapped between machines made by different manufacturers. This wasn't mass production yet. That concept emerged later. But the machinery was already modular. The same principle appears in British factories. Steam engines built in Manchester fit mounting points designed in Birmingham. Boilers manufactured in Sheffield connected to pipe systems laid in Liverpool. The components were compatible before compatibility was economically necessary. Agricultural equipment follows the pattern. The mechanical reaper, patented in 1834, was designed with standardized blade widths and gear ratios. Early models were built by different blacksmiths in different states, yet the designs converged on identical specifications. By the 1850s, reapers were interchangeable. Farmers could buy replacement parts from multiple suppliers. The parts fit. This wasn't market standardization. The market was too small, too regional. Yet the equipment was built as if a unified supply chain already existed. Water infrastructure reveals the deepest consistency. Aqueducts built in the 1830s and 1840s, in New York, Philadelphia, Boston, and London, used nearly identical engineering principles. Gravity-fed systems, standardized pipe diameters, comparable flow rates. The Croton Aqueduct, completed in New York in 1842, could deliver 90 million gallons per day. The city's population required 30 million. The system was built for 3 times the demand. London's Thames Tunnel, completed in 1843, was the first underwater tunnel in the world. It was designed for heavy vehicle traffic. But in 1843, there was no need for such a tunnel. The foot traffic didn't justify the cost. Decades later, it carried trains. The tunnel hadn't been repurposed. It had been used as intended. The cumulative weight of these examples creates pressure. Canal systems built before cargo existed. Railways laid before populations arrived. Telegraph networks installed before communication demand. Ports designed for ships not yet sailing. Administrative systems synchronized without coordination. Each example alone is explainable. Economic foresight. Entrepreneurial optimism. Convergent engineering. But together they form a pattern. Infrastructure that anticipates. Systems that inherit rather than innovate. Standardization without centralization. Whether this reflects remnants of older systems or parallel development driven by shared knowledge remains unresolved. But the timing, clustered around 1816, and the scale demand attention. The word Tartaria appears on European maps as early as the 13th century. It wasn't a country. It was a geographic designation, a vast territory stretching across Central Asia and Siberia. The term derived from Tatar, referring to Turkic and Mongol peoples who inhabited the region. By the 18th century, cartographers used Tartary to label areas beyond European political control. Grand Tartary, Chinese Tartary, Independent Tartary. The labels marked spaces, not states. The term disappeared from maps by the mid-19th century, not because a civilization collapsed but because European knowledge expanded. As empires pushed eastward, the vague designation fractured into recognized nations and provinces. No historical record describes a unified Tartarian empire. No archaeological consensus supports a globe-spanning civilization erased from history. But the word persisted in another form. In the 2010s, online researchers began reinterpreting architectural and infrastructural anomalies through a different lens. Buildings with similar neoclassical features across continents. Infrastructure projects that seem to anticipate future needs. Administrative systems that emerged in parallel. The hypothesis proposed: these weren't coincidences or convergent evolution. They were remnants. The reinterpreted Tartaria became a framework, a way to explain synchronicities in 19th century development that conventional history treats as independent innovations. The evidence cited includes the patterns explored here. Infrastructure before demand. Overengineered systems. Standardization without centralization. 3 interpretations have emerged. The inheritance model. This perspective suggests that 19th century industrialization wasn't entirely new. Instead, engineers and planners worked from older templates, technical knowledge, architectural principles, or surviving infrastructure from a previous cycle of development. The model doesn't require a lost empire. It proposes that pockets of advanced capability existed before the commonly accepted timeline, and that knowledge filtered into 19th century projects through documentation, artifacts, or oral transmission. Evidence cited: the precision of early infrastructure, the speed of standardization, the architectural consistency across regions with limited communication. The Erie Canal's locked dimensions, Britain's railway gauge, telegraph protocols, grain elevator designs. Each could represent inherited specifications rather than original innovation. Under this model, 1816 becomes significant not as a starting point, but as a reset point. The global climate disruption forced reconstruction, and reconstruction revealed underlying templates. The coordinated development model. This interpretation focuses on hidden coordination. It suggests that 19th century infrastructure projects weren't independent entrepreneurial ventures but components of a larger plan system. The model proposes that a network of engineers, financiers, or planners operated across national boundaries, implementing a unified vision. The standardization wasn't accidental. It was designed.